Tonight, we're going to explore a truth that most people don't want to hear. One that Hollywood refuses to accept. One that challenges more than a century of science fiction dreams and futuristic promises. We will never truly travel among the stars. Not in your lifetime. Not in your children's lifetime. Not in 10,000 years. The stars are separated from us by distances so vast, energies so extreme, and physical barriers so fundamental that they may forever remain unreachable to biological civilization. And by the end of tonight, you're going to understand exactly why the dream of casually exploring the galaxy, visiting distant solar systems, and building civilizations across the Milky Way may be one of the greatest illusions humanity has ever created. Before we begin, if you enjoy exploring the universe, the mysteries of physics, and the true scale of reality, consider liking the video or subscribing to the channel. It genuinely helps more curious minds discover content like this. Now, let's begin. To understand why interstellar travel is likely impossible, we first need to understand something most people completely misunderstand about space itself. Space is not an ocean. It is not a frontier similar to the American West. It is not the next Antarctica. And it is not simply aviation scaled upward. Throughout history, humans conquered nearly every environment on Earth because Earth always provided survival pathways. When ancient sailors crossed oceans, they still had access to air, gravity, food sources, weather systems, and islands where they could stop and recover. Even the harshest deserts on Earth still contain an atmosphere humans can breathe. Even Antarctica still has gravity, water in frozen form, and rescue possibilities. But space offers none of these things. Space is not hostile in the way a desert or storm is hostile. Space is fundamentally incompatible with human biology. The vacuum of space will kill an unprotected human in seconds. There is no oxygen, no atmospheric pressure, no naturally available food, no naturally available liquid water, no protection from radiation, no magnetic field, no breathable environment. And unlike every frontier humans explored throughout history, there are no natural checkpoints between stars. No islands. No ports. No civilizations. No rescue missions. Nothing. Just darkness stretching across trillions upon trillions of miles. The comparison between crossing oceans and traveling between stars is so inaccurate that it completely hides the true scale of the problem. Imagine if crossing the Atlantic Ocean required traveling not for weeks, but for tens of thousands of years. Imagine if the ocean itself instantly killed you the moment your ship failed. Imagine if every grain of sand moving toward your vessel struck with the energy of a bomb. Imagine if communication with home took years. Imagine if no rescue was possible under any circumstances. That is far closer to what interstellar travel actually means. Now let's examine the nearest star system to Earth. The closest star beyond our Sun is Proxima Centauri, part of the Alpha Centauri system. It sits approximately 4.24 light-years away. That number sounds small because we're used to thinking in miles or kilometers. But a light-year is enormous. A single light-year equals nearly 5.9 trillion miles. That means Proxima Centauri is about 25 trillion miles away. 25 trillion. To understand how absurd that distance really is, let's scale downward. Light can circle Earth more than 7 times in a single second. Now let's examine the fastest human-made object ever built. The Parker Solar Probe, launched by NASA in 2018, reaches speeds exceeding 430,000 miles per hour during close approaches to the Sun. That speed is extraordinary. At that velocity, you could travel around Earth in roughly 3 minutes. But even at that incredible speed, the probe would still require over 6,000 years to reach Proxima Centauri. 6,000 years. Human civilization itself is only about 6,000 years removed from the invention of early writing systems. When that hypothetical journey began, the pyramids had not yet been constructed. Ancient Rome did not exist. Modern nations did not exist. Nearly all of recorded human history would unfold while the spacecraft drifted silently through interstellar darkness. And remember, that's merely the nearest star. Now some people argue that technology always improves. And they're right. Technology does improve. The Wright brothers flew in 1903. Humans walked on the moon only 66 years later. But progress only works within the boundaries allowed by physics. No amount of technological advancement will allow humans to breathe underwater without equipment. No amount of engineering allows perpetual motion machines. And no amount of progress may ever overcome the energy requirements of relativistic travel. This distinction is critical. Human history contains many engineering limitations that later disappeared. But physical laws are different. They do not negotiate. Let's examine the energy problem directly. The kinetic energy equation is simple. Energy equals 1/2 mass times velocity squared. That final term matters enormously. Velocity squared means doubling speed requires 4 times more energy. Increasing speed by 10 times requires 100 times more energy. As spacecraft approach relativistic speeds, the required energy becomes almost incomprehensible. Now imagine a true interstellar human spacecraft. But even those designs required tens of thousands of tons of fusion fuel just to accelerate relatively small unmanned probes. Not cities. Not human colonies. Tiny robotic missions. And fusion itself remains experimental. Humanity still does not possess practical commercial fusion reactors after decades of research. We are discussing a technology we have not yet mastered even for electrical power generation on Earth, let alone for starships. Then comes antimatter. Theoretically, antimatter is the most energy-dense fuel possible. Matter-antimatter annihilation converts mass directly into energy according to Einstein's famous equation. E equals mc squared. 1 kilogram of antimatter annihilating with 1 kilogram of normal matter would release energy equivalent to tens of millions of tons of TNT. Far beyond nuclear weapons. This makes antimatter attractive in theory. But reality is brutal. Antimatter does not naturally exist in useful quantities. We must manufacture it inside particle accelerators. And producing antimatter is catastrophically inefficient. Modern facilities use vastly more energy creating antimatter than the antimatter itself later releases. Humanity has only produced microscopic quantities in laboratory conditions. Far less than a gram. and storing antimatter may be even harder than producing it. The moment antimatter touches ordinary matter, annihilation occurs instantly, which means you cannot place antimatter inside normal containers. It must be suspended in electromagnetic traps. If containment fails even briefly, the resulting explosion could destroy the spacecraft. An interstellar antimatter ship would effectively travel through space carrying one of the most dangerous explosive systems imaginable. And this still does not solve the deeper issue. Even antimatter propulsion does not break the light-speed barrier. It only reduces travel times from thousands of years to decades. The stars remain staggeringly far apart. Now let's discuss one of the most underestimated dangers in interstellar travel: radiation. Earth is protected by two extraordinary shields: our atmosphere and our magnetic field. Together they block enormous amounts of cosmic radiation and charged particles. Outside that protection, space becomes far more dangerous. Astronauts aboard the International Space Station already experience significantly higher radiation exposure than humans on Earth. A journey lasting decades through interstellar space would expose crews to enormous cumulative radiation doses. Cosmic rays are especially dangerous. These are ultra-high energy particles traveling close to light speed. Some originate from supernova explosions. Others may come from black holes or extreme astrophysical events. When these particles strike human tissue, they damage DNA at the molecular level, increasing cancer risk, damaging organs, potentially affecting cognition and fertility. And radiation shielding is heavy. Very heavy. Water helps shield radiation. Lead helps shield radiation. Dense materials work best. But adding shielding increases spacecraft mass dramatically, which then increases propulsion requirements, which then requires more fuel, which increases mass again. Every solution worsens another problem. And then we encounter another terrifying issue: interstellar dust. Space is not truly empty. Between stars exist sparse clouds of gas and microscopic particles. At normal speeds, these particles are insignificant. But at relativistic velocities, they become deadly. A tiny grain of dust impacting a spacecraft traveling at 20% of light speed would strike with explosive force. Over years or decades, repeated impacts could gradually destroy the vessel. Shielding against this requires even more mass. Again, the same cycle repeats. Every protection system makes the spacecraft heavier. And heavier spacecraft require exponentially more energy. Now let's move beyond engineering and discuss human biology itself. Humans evolved under Earth's gravity. Our muscles and bones depend on continuous mechanical stress. In microgravity, the human body deteriorates rapidly. Astronauts lose bone density. Muscle mass declines. Vision problems emerge. Fluid distribution changes. The cardiovascular system weakens. Even with exercise, long-duration spaceflight causes major health effects. A mission lasting decades would require artificial gravity, likely through rotation. But constructing enormous rotating habitats adds tremendous engineering complexity and mass. Then there is psychology. Imagine spending your entire life inside a metal structure drifting through darkness. No open sky. No forests. No oceans. No natural weather. No real horizon. No freedom to leave. Studies in isolated environments already show increased depression, anxiety, conflict, and psychological strain. And those studies involve months, not generations. Now imagine a generation ship. Children born aboard. Grandchildren born aboard. Entire civilizations trapped inside an artificial world. Human history suggests closed societies are unstable. Political extremism emerges. Religious conflict emerges. Social fragmentation emerges. Even on Earth, civilizations collapse regularly. And Earth contains vast ecosystems, abundant resources, and escape possibilities. A generation ship contains none of those things. A single serious conflict could doom everyone. A single system's failure could end the mission permanently. The margin for error approaches zero. Now let's discuss faster-than-light travel, the ultimate science fiction solution. Warp drives. Hyperspace. Wormholes. Subspace. These concepts dominate science fiction because without them, galactic civilization becomes nearly impossible. But there is currently no evidence faster-than-light travel can physically exist. Some solutions to Einstein's field equations mathematically allow warped spacetime or wormholes. But these solutions require exotic matter with negative energy density. Matter unlike anything humanity has ever produced or observed in usable form, and the required energies may rival those of stars themselves. Some calculations suggest warp drive concepts would require more energy than exists in entire planets. Others appear fundamentally unstable. And faster-than-light travel creates profound causality problems. If information can travel faster than light, then under certain reference frames effects can precede causes. The logical structure of reality begins breaking down. This is why many physicists believe faster-than-light travel is not merely difficult, but impossible. And if that is true, then the implications are staggering. The galaxy is effectively uncrossable. Even at 10% of light speed, crossing the Milky Way would require roughly 1 million years. Longer than modern humans have existed. Civilizations may simply never spread across galaxies in the way science fiction imagines. Perhaps every intelligent species remains permanently trapped near its home star, separated from all others by time, energy, and physics itself. And that possibility may explain one of the greatest mysteries in science: the Fermi paradox. If intelligent life is common, where is everybody? Why don't we see giant galactic civilizations? Why don't alien ships fill the skies? Perhaps because interstellar travel is fundamentally impractical. Perhaps every civilization eventually discovers the same terrible truth. The stars are too far away. Not emotionally, physically. Maybe the universe is not designed for civilizations to spread freely between stars. Maybe intelligence evolves locally but remains isolated cosmically. An archipelago of lonely worlds separated by impossible oceans of spacetime. And if that is true, then humanity's future changes completely. Our destiny may not be conquering the galaxy. It may be surviving here, protecting Earth, expanding carefully through our own solar system. Because compared to interstellar space, our solar system is astonishingly close. Mars is reachable. The moons of Jupiter and Saturn may someday host scientific outposts. Asteroid mining may become real. Humanity could still spread across the solar system over centuries. But the stars themselves may remain forever beyond reach. And perhaps the most important realization is this: the universe does not owe us accessibility. We evolved emotionally expecting frontiers because every frontier in human history eventually yielded to exploration. But cosmic scale may represent a boundary no civilization can truly cross. And maybe accepting that reality is part of maturity as an intelligent species. The stars are still beautiful, still meaningful, still worth studying, but perhaps not conquerable. When you look at the night sky tonight, think about what those stars truly are, not nearby destinations waiting for tourists, but ancient suns separated by gulfs of time so vast that even light struggles to cross them. The universe is not small. It is not human-scaled, but perhaps not conquerable. When you look at the night sky tonight, think about what those stars truly are. Not nearby destinations waiting for tourists, but ancient suns separated by gulfs of time so vast that even light struggles to cross them. The universe is not small. It is not human-scaled. It is not built around our ambitions. And maybe the greatest achievement of intelligence is not conquering the cosmos, but understanding how immense it really is, because even confined to one solar system, humanity still has more worlds to explore than entire generations could ever fully understand. The Moon, Mars, Europa, Titan, the Kuiper Belt, the Oort cloud. Our own cosmic neighborhood alone contains enough mystery to occupy humanity for thousands of years. The universe remains magnificent even if the stars themselves remain forever out of reach. And perhaps that is the final truth. The dream of interstellar travel was never really about transportation. It was about hope, about transcendence, about escaping the limits of being human. But the universe may not allow escape from every limit. Some boundaries are not technological. They are woven into reality itself. And the speed of light may be one of them. Over a 50-year journey, even the most basic human needs become staggering engineering problems. A crew of just 100 people would require enormous reserves of food, water, oxygen, medicine, spare equipment, and energy simply to stay alive. Food alone becomes almost unimaginable at interstellar scales. If each person consumes roughly 1 kilogram of food per day, then over 50 years you need more than 1.8 million kilograms of food. More than 1,800 tons. And that estimate assumes near-perfect preservation with no spoilage, no contamination, no crop failure, and no packaging losses. In reality, long-term food storage is incredibly difficult. Vitamins degrade over time. Nutritional quality slowly breaks down. Even freeze-dried food cannot remain perfectly stable for half a century without careful environmental control. Water becomes an even greater challenge. Humans need water not just for drinking, but for cooking, cleaning, hygiene, medical procedures, cooling systems, and potentially agriculture. Modern life on Earth uses hundreds of liters per person every day when all systems are included. Even an aggressively efficient spacecraft might reduce total usage to around 50 liters per person per day through extreme recycling and conservation. Yet over a 50-year mission with 100 people, that still amounts to more than 91 million liters of water. Over 91,000 tons. Far too massive to simply carry aboard a spacecraft. That means any realistic interstellar vessel would require an almost perfectly closed-loop life support system. Every drop of water would need to be recovered and purified continuously. Sweat, urine, condensation from breath, water used for washing, moisture released from plants, all of it would need to be captured and recycled indefinitely. The International Space Station already performs a simplified version of this process. NASA's Environmental Control and Life Support System can recycle roughly 90% of onboard water through filtration, catalytic oxidation, and vapor compression distillation. But even that leaves losses. Small inefficiencies accumulate over time. Over decades, even a tiny annual loss becomes catastrophic. Perfect recycling is impossible because of thermodynamics. Entropy guarantees losses somewhere in the system. Filters wear out. Molecules escape. Chemical contaminants build up. Mechanical systems degrade. Every recycling loop requires energy, maintenance, and replacement parts. The longer the mission lasts, the more dangerous even tiny inefficiencies become. Air presents similar problems. Humans constantly exhale carbon dioxide, which quickly becomes toxic in enclosed environments. On Earth, the biosphere naturally balances oxygen and carbon dioxide through photosynthesis, ocean chemistry, and planetary scale cycles refined over billions of years. Inside a spacecraft, those planetary systems must be artificially recreated on a miniature scale. Carbon dioxide scrubbers would need to operate continuously for generations. Oxygen would need constant replenishment through electrolysis, chemical processing, or biological systems like plants and algae. The ISS currently uses systems such as the carbon dioxide removal assembly and oxygen generators that split water molecules into hydrogen and oxygen. Some systems also use the Sabatier reaction, combining captured carbon dioxide with hydrogen to produce methane and water. This improves efficiency, but still does not fully close the loop. Every process consumes energy and creates waste heat. Every machine contains moving parts that eventually fail. For truly long-duration missions, biological systems would likely become essential. Plants could help recycle carbon dioxide while simultaneously producing food. Hydroponic and aeroponic farming systems might sustain portions of the crew's diet. But agriculture in space introduces enormous complexity. Plants require precise lighting, nutrient delivery, pollination systems, humidity regulation, atmospheric control, and disease prevention. On Earth, agriculture works because it relies on massive planetary support systems. Soil ecosystems contain billions of microorganisms. Weather cycles distribute water. Bees and insects pollinate crops. Entire ecological networks stabilize the environment. A spacecraft has none of those natural buffers. A fungal outbreak or bacterial infection inside a closed agricultural module could destroy the food supply of an entire generation ship. And unlike Earth, there are no neighboring farms to compensate for failed harvests. No supply chains. No imports. If crops fail in deep space, people starve. That means crews would require massive genetic seed banks, frozen embryos, redundant crop varieties, and extensive agricultural expertise. Future generations aboard the ship would need to preserve not only biological diversity, but technical knowledge itself. Botanists would need to train new botanists. Engineers would need to train new engineers. Doctors would need to educate future doctors. Entire professional systems would need to survive uninterrupted for centuries. Human history shows how fragile knowledge can be. Civilizations on Earth have repeatedly lost technologies and scientific understanding. After the fall of the Western Roman Empire, advanced engineering methods disappeared for centuries. Ancient construction techniques, metallurgy, and mathematics were forgotten. The burning of the Library of Alexandria destroyed immeasurable amounts of knowledge forever. On a generation ship, the consequences would be even more severe. If critical expertise disappears, there is no outside civilization to rediscover it from. No universities. No libraries beyond what the ship carries. A single cultural collapse could doom the mission permanently. Then there is the problem of maintaining the spacecraft itself. Every machine eventually breaks. Bearings wear down. Electronics degrade. Radiation damages circuits. Seals crack. Metals fatigue under stress. Plastics become brittle over time. On Earth, replacement parts can be manufactured globally and delivered quickly. In interstellar space, every spare component must either be carried from launch or manufactured on board. That means the spacecraft would effectively need to contain an entire industrial civilization inside itself. Machine shops. Fabrication systems. Raw materials. 3D printers. Metallurgical facilities. Chemical processing equipment. Mining systems for recycling internal materials. Every layer of redundancy adds mass, complexity, and additional failure points. And no matter how much redundancy exists, catastrophic failures remain possible. A reactor malfunction. A hull breach from micrometeoroids. A disease outbreak. Psychological collapse among the crew. Power system failures. Ecological imbalance. Over decades or centuries, low-probability disasters eventually become statistical inevitabilities. This is one reason fully closed ecosystems remain so difficult even on Earth. Biosphere 2 in Arizona attempted to create a sealed artificial ecosystem during the 1990s. 8 people lived inside the facility while scientists attempted to sustain a balanced miniature biosphere. Despite access to Earth's gravity, sunlight, outside monitoring, and emergency intervention, the experiment struggled severely. Oxygen levels dropped unexpectedly. Food production failed to meet expectations. Ecological imbalances emerged rapidly. Some species exploded in population while others vanished. And that experiment lasted only 2 years. A generation ship would need to maintain ecological stability not for years, but for decades or centuries in one of the harshest environments imaginable. Then there is radiation, one of the deadliest hazards in space. Earth's atmosphere and magnetic field shield us from most cosmic radiation. Outside that protective bubble, deep space becomes extremely dangerous. Solar particles, galactic cosmic rays, and high-energy atomic nuclei constantly bombard spacecraft traveling between stars. Solar flares and coronal mass ejections can unleash intense bursts of charged particles capable of delivering lethal radiation doses in hours. Astronauts aboard the ISS already receive significantly more radiation exposure than humans on Earth, despite still being partially protected by Earth's magnetosphere. Galactic cosmic rays are even more dangerous. These particles are accelerated by supernova explosions and other violent astrophysical events to velocities approaching the speed of light. Some carry enormous kinetic energy concentrated into single atomic nuclei. When these particles strike matter, they create cascades of secondary radiation capable of penetrating deep into spacecraft structures and human tissue. Radiation damages DNA. It increases cancer risk. It can cause neurological damage, reproductive harm, and long-term degeneration of organs and tissues. Studies of astronauts already show elevated cancer risks after relatively short missions lasting only months. Now imagine exposure lasting decades. Shielding helps, but shielding introduces enormous mass penalties. Water is an excellent radiation shield because hydrogen-rich materials absorb energetic particles efficiently. But water is heavy. Surrounding a habitat module with sufficient water shielding would require thousands upon thousands of tons. Lead blocks certain forms of radiation effectively, but its density makes it nearly impossible for interstellar spacecraft. Advanced proposals suggest magnetic shielding systems that generate artificial magnetospheres around ships, but these require superconducting magnets and enormous power generation systems. Even worse, radiation damages electronics too. Cosmic rays can flip memory bits in computers, corrupt software, and slowly degrade semiconductors. Spacecraft systems would require hardened electronics, redundant computing systems, error correction protocols, and constant maintenance. Over decades, even hardened systems accumulate damage. And then comes navigation. Space may appear empty, but it is filled with dust grains, atoms, and microscopic debris. At ordinary spacecraft velocities, this is manageable. But at relativistic speeds, tiny particles become catastrophic projectiles. At 10% the speed of light, even microscopic dust grains carry extraordinary kinetic energy. A tiny particle impacting the spacecraft could release energy comparable to explosives. Larger debris could completely destroy the vessel instantly. Interstellar hydrogen atoms themselves become dangerous at high velocities. A spacecraft moving through interstellar space at relativistic speeds effectively experiences a constant stream of high-energy particle impacts. Forward surfaces erode. Heat accumulates. Shielding slowly degrades. Detecting and avoiding obstacles becomes nearly impossible because of reaction time limits. At relativistic speeds, by the time sensors detect an object ahead, there may not be enough time to maneuver. Then relativity itself introduces bizarre consequences. According to Einstein's special relativity, time slows down for travelers moving near light speed relative to stationary observers. At 90% the speed of light, time passes far more slowly aboard the spacecraft than on Earth. A crew traveling to a star 50 light-years away might experience only a fraction of the time that passes on Earth. When they arrive, decades or centuries may have elapsed back home. If they ever returned, everyone they knew would be gone. Entire civilizations might have changed beyond recognition. Interstellar travel becomes not just travel through space, but travel through time. Communication becomes nearly meaningless over such distances. Radio messages themselves require years or decades to cross interstellar space. Conversations would span generations. And even if humanity somehow overcomes every previous obstacle, there remains the question of destination worlds. Most star systems likely do not contain Earth-like planets. Many exoplanets orbit too close to their stars, becoming scorched wastelands. Others are frozen worlds far beyond habitable zones. Some orbit unstable stars that unleash frequent radiation storms. Many lack magnetic fields or breathable atmospheres. Even seemingly habitable planets may possess toxic chemistry, crushing gravity, lethal microbes, or unstable climates. Some could already contain alien life, raising immense ethical and biological risks. Colonists arriving after generations of travel would face entirely alien environments with no possibility of rescue or resupply. If settlement fails, extinction follows. Science fiction often imagines solutions like warp drives and wormholes, but according to modern physics, these ideas remain highly speculative and may be fundamentally impossible. Concepts such as the Alcubierre warp drive require exotic negative energy matter that has never been observed. Traversable wormholes may violate causality itself, potentially allowing paradoxical time travel. The speed of light appears deeply embedded into the structure of space-time as a hard cosmic speed limit. And perhaps that explains one of the universe's greatest mysteries, the Fermi paradox. If intelligent civilizations are common, where is everyone? Maybe civilizations repeatedly discover the same truth. The universe is simply too vast. Interstellar travel may be prohibitively expensive, dangerous, slow, and physically constrained by fundamental laws. Perhaps every civilization becomes isolated inside its own stellar neighborhood, forever separated from others by impossible distances. The galaxy could be filled with intelligent life, each civilization trapped within its own island of stars, never able to truly meet. That possibility is both haunting and strangely beautiful. Because even if humanity never travels among the stars physically, we are still capable of understanding them. Through telescopes, spectroscopy, mathematics, and science, we have already uncovered the history of galaxies billions of light-years away. We have discovered exoplanets, black holes, gravitational waves, dark matter, and the expanding universe itself. We are creatures made of atoms forged inside ancient stars. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all originated in stellar furnaces billions of years ago. We are literally made of stardust. But there is another problem interstellar travel introduces, one that goes beyond engineering, physics, biology, or even survival. It is the problem of identity. What happens psychologically and culturally to human beings who are born aboard a ship that will never see Earth? What happens to a civilization that exists entirely inside metal walls drifting through the darkness between stars? The first generation aboard a generation ship would still remember Earth. They would remember oceans, wind, rain, forests, cities, open skies, gravity that felt natural beneath their feet. They would remember birds flying overhead and sunsets spreading across entire horizons. Even if they volunteered willingly for the mission, they would carry with them a deep awareness of loss. They would know they were leaving behind the only true home humanity had ever known. But their children would not. A child born aboard a generation ship would experience the spacecraft itself as reality. Artificial corridors would feel normal. Recycled air would smell normal. The constant background hum of machinery would become the sound of life itself. Earth would not be a memory to them, it would be mythology. A distant ancestral world they had never seen and never could see. By the third or fourth generation, Earth might feel almost fictional. Think about how quickly cultures change even on Earth. Languages evolve dramatically over only a few centuries. Social values shift. Religions fragment. Political systems rise and collapse. Historical events become distorted through storytelling and incomplete records. Now imagine a closed society isolated for 100 years, 200 years, perhaps longer. No immigration, no outside communication except delayed radio transmissions arriving years after being sent. No contact with broader humanity. The people aboard the ship would slowly become culturally distinct from Earth. Their traditions would evolve around the ship itself. Their myths and rituals might center on maintenance cycles, reactor systems, agricultural harvests, and the sacred importance of life support machinery. Entire philosophies could emerge around preserving the vessel because the vessel is literally their world. Future generations might not even agree with the mission anymore. This creates a profound ethical problem. The original crew chooses the journey voluntarily, but the generations born afterward never consented. They are born into confinement with no possibility of leaving. They inherit a mission chosen by ancestors long dead. Would they still believe reaching another star matters? Or would they question why they should dedicate their lives to a destination they will never personally experience? A generation ship could face political unrest, ideological divisions, even civil conflict. Some factions might want to continue toward the target star. Others might argue for turning back if possible. Others might reject the mission entirely and decide the ship itself is humanity's permanent home. The sociology becomes almost impossible to predict. Human psychology evolved for open environments on a living planet. For millions of years our ancestors lived beneath vast skies, surrounded by ecosystems filled with natural sensory input. Sunlight regulated circadian rhythms. Changing seasons structured time. Rivers, mountains, storms, and landscapes provided constant variation. A spacecraft offers none of that naturally. Even with advanced virtual reality systems and artificial habitats, people would still know they are confined inside an engineered structure floating through lethal emptiness. There would be no true wilderness, no untouched environments. Every breath, every meal, Every watt of power would depend on fragile machinery maintained by human hands. The psychological burden could be immense. We already see signs of this during long-duration isolation experiments on Earth. Researchers stationed in Antarctica often report depression, interpersonal conflict, anxiety, sleep disorders, and emotional fatigue despite having communication with the outside world and knowing they can eventually leave. Submarine crews experience similar pressures during extended deployments underwater. Astronauts aboard the International Space Station undergo strict psychological screening because even relatively short missions can create stress, tension, and cognitive strain. Now extend that isolation across generations. There is also the issue of population genetics. A generation ship cannot carry billions of people. Most realistic concepts involve populations ranging from a few hundred to perhaps several thousand individuals. But small populations face serious genetic risks over long timescales. Inbreeding becomes dangerous if genetic diversity drops too low. Harmful mutations can accumulate. Certain hereditary diseases may become increasingly common. Maintaining a healthy gene pool would require careful reproductive planning, genetic monitoring, possibly frozen embryo banks, and advanced reproductive technologies. And even then, unpredictable genetic drift could occur over centuries. Different gravity environments would further complicate matters. Humans evolved under Earth's gravity. In reduced gravity, muscles weaken, bones lose density, cardiovascular systems change, and developmental processes may be altered. Children born in artificial gravity systems might experience unknown long-term effects depending on the rotation rate and habitat design. No one knows how multiple generations of humans would adapt biologically to life entirely in space. Perhaps after centuries, generation ship populations would no longer be physiologically identical to Earth humans. And while all of this is happening internally, the external universe remains unimaginably hostile. Interstellar space is cold beyond ordinary human intuition. The average background temperature of the universe is only about 2.7 Kelvin above absolute zero. Barely warmer than the leftover radiation from the Big Bang itself. A spacecraft traveling between stars exists inside near-perfect darkness and near-perfect vacuum for decades. There would be long stretches where the destination star is still just another bright point among thousands of others. No nearby planets. No rescue. No landmarks. Only the silent blackness between stars. That isolation changes how we usually think about exploration. Throughout human history, exploration always occurred within connected systems. Sailors crossing oceans still traveled on the same planet. They could resupply, establish colonies, return home, or encounter other civilizations. Interstellar travel breaks that model completely. The distances are simply too vast. The nearest star system, Alpha Centauri, is over 4 light-years away. That sounds manageable until you realize light itself, the fastest thing physically possible, requires more than 4 years to cross that distance. Voyager 1, the fastest spacecraft humanity has ever launched, would need over 70,000 years to reach Alpha Centauri if it were headed in that direction. 70,000 years. Human civilization itself is younger than that. And Alpha Centauri is our nearest neighboring star. The Milky Way galaxy contains hundreds of billions of stars spread across roughly 100,000 light-years. Even traveling at relativistic speeds, crossing substantial portions of the galaxy would require timescales longer than recorded human history. Other galaxies are incomprehensibly farther away. The Andromeda Galaxy, the nearest major galaxy to ours, is about 2.5 million light-years away. Even light requires millions of years to travel between galaxies. This means humanity is probably not becoming a galaxy-spanning civilization in the science fiction sense. The universe is not structured for easy expansion. It is structured around separation. And perhaps that changes how we should think about our future. For centuries, human civilization operated under assumptions of endless expansion. New continents, new resources, new frontiers. The stars became the ultimate symbolic frontier in modern culture. Entire generations grew up imagining humanity spreading endlessly outward through the galaxy, but reality may force a different philosophy. Instead of expansion, perhaps the future is about stewardship. If Earth and the solar system are effectively our permanent home, then preserving them becomes infinitely more important. Climate stability, ecological sustainability, long-term civilization planning, planetary defense against asteroids, responsible resource management, and peaceful global cooperation become existential priorities. Because there may not be another Earth waiting for us somewhere else. Mars, for example, is often imagined as a backup planet for humanity. But Mars is extraordinarily hostile. Its atmosphere is less than 1% as dense as Earth's. Surface radiation levels are dangerously high. Temperatures plunge far below freezing. Liquid water is unstable on the surface. The soil contains toxic perchlorates. Even optimistic terraforming concepts would likely require centuries or millennia of engineering on a planetary scale. And yet Mars is still vastly easier to reach and settle than another star system. This is why many scientists increasingly believe humanity's realistic future lies not in interstellar empires, but in becoming a highly advanced solar system civilization. Orbital habitats, lunar industries, Martian research settlements, mining operations in the asteroid belt, scientific outposts on icy moons like Europa, Titan, and Enceladus. The solar system alone contains more resources than humanity could likely use for millions of years. The asteroid belt contains immense quantities of metals and minerals. Gas giants possess enormous reserves of hydrogen and helium. Some moons may contain subsurface oceans with more total water than Earth itself. And all of it remains within a region measured in light hours rather than light years. Communication delays inside the solar system are inconvenient but manageable. Travel times are measured in months, not centuries. Rescue missions remain possible. Trade and coordination can still function. In many ways, the solar system may already be more than enough for an advanced civilization. And yet the stars will continue calling to us emotionally. Because the desire to explore is deeply human. When ancient humans looked beyond the horizon, they did not know what they would find. Exploration is woven into our psychology. Curiosity helped our species survive. It pushed us across continents, across oceans, eventually into space itself. That instinct will never disappear. Even if humans never physically walk among distant stars, we will still explore them intellectually. Future telescopes may directly image Earth-like exoplanets with extraordinary detail. We may map alien continents, detect weather systems on distant worlds, analyze atmospheric chemistry, and search for biosignatures indicating life. One day we may discover undeniable evidence that biology exists elsewhere in the universe. Imagine detecting oxygen, methane, and industrial pollutants simultaneously in an exoplanet atmosphere. Imagine receiving structured radio signals containing mathematical patterns impossible to explain naturally. Imagine discovering another civilization separated from us by dozens or hundreds of light years. That discovery alone would permanently transform human civilization. For the first time in history, humanity would know with certainty that intelligence evolved somewhere else in the cosmos. And even if we could never meet physically, communication itself might still become possible. Slow. Delayed by years or centuries. But possible. Entire conversations between civilizations might unfold across generations. A message sent from Earth might receive a reply centuries later. The original senders would be long dead, but the exchange itself would continue. Knowledge could accumulate slowly across the stars. Mathematics, physics, philosophy, art, music encoded into radio transmissions traveling through the galaxy. Perhaps that is the true future of intelligent life in the universe. Not empires spreading physically across the stars, but networks of distant civilizations exchanging knowledge across immense gulfs of time and space. A cosmic conversation rather than cosmic conquest. And there is something strangely beautiful about that idea. Because it means intelligence matters not because it dominates the universe physically, but because it understands it. The universe does not appear designed for comfort or convenience. Most of space is deadly vacuum. Most planets are hostile. Black holes consume matter silently. Stars explode. Galaxies collide. Time itself stretches across scales the human brain struggles to comprehend. And yet within this immense and indifferent cosmos, matter arranged itself into living cells. Those cells evolved into organisms capable of memory, language, imagination, and science. The atoms inside your body were forged in stars that died before the sun even existed. The calcium in your bones, the oxygen in your lungs, the phosphorus in your DNA, all emerged from ancient stellar furnaces billions of years ago. In a literal sense, every human being is connected to cosmic history. We are temporary structures built from ancient matter, capable of contemplating the universe that created us. And perhaps that is enough. Perhaps understanding the cosmos is itself one of the highest achievements possible for any civilization. Not conquering galaxies, not outrunning light, but becoming aware. Becoming capable of wonder. Because the universe may be unimaginably vast, cold, and difficult to cross. But through science, consciousness, and curiosity, part of that universe has learned to look back at itself and ask why it exists at all.